Weather influences our everyday activities, our jobs, and our health and comfort. There are few aspects of our physical environment that affect our lives more than the weather. Which of these weather phenomena have you experienced? The United States has the greatest variety of weather of any country in the world. Taken together, severe weather events are more frequent and damaging in the United States than in any other nation. This graph shows average annual storm-related deaths in the United States for the 30-year span from 1977 to 2006. Which bar on the graph do you think represents annual number of deaths from these four types of severe weather? Between 2004 and 2006, the United States experienced 12 weather events in which overall damages and costs reached or exceeded $1 billion. In addition to its direct impact on people, weather has a strong effect on the world economy by influencing agriculture, transportation, industry, energy use, water resources, and more. The atmosphere obviously influences our lives a great deal. It is also important to realize that people influence the atmosphere as well. Air pollution, acid rain, ozone depletion, and global warming are all examples of the impact of people on the atmosphere. Anyone who has ascended a high mountain or listened to a pilot report the temperature outside an airplane knows that air temperature usually drops with an increase in altitude. Do temperatures continue to drop all the way from the surface to the top of the atmosphere? The answer is no. Temperatures actually fluctuate with increasing distance from Earth's surface. The atmosphere is divided vertically into 4 layers on the basis of temperature. The bottom layer in which we live is called the troposphere. The term troposphere is derived from the Greek word tropos and is a reference to the appreciable vertical mixing of air in this layer. The main source of energy for the atmosphere is radiation emitted from Earth's surface. In the troposphere, the farther we get from Earth's surface, the lower the air temperature. How many degrees does the temperature drop from Earth's surface to a height of 11 kilometers? Calculate the average drop in temperature from 0 kilometers to 11 kilometers. Remember that you already know that the total drop in temperature is 72 degrees Celsius. Pick the correct answer. The vertical temperature change in the troposphere is known as the environmental lapse rate. It is a variable figure, but its average value is 6.5 degrees Celsius per kilometer. The actual environmental lapse rate is determined by using a radiosonde, which is an instrument package attached to a balloon that transmits data by radio as it ascends through the troposphere. The decrease in temperature continues to an average height of 11 or 12 kilometers. This upper boundary of the troposphere is called the tropopause. Beyond the troposphere is the stratosphere. Here, temperatures level off and then gradually increase to an altitude of about 50 kilometers. Why do temperatures rise in the stratosphere despite the fact we are getting farther from Earth's surface? The reason for the higher temperatures in the stratosphere is that the atmosphere's ozone is concentrated in this layer. Ozone is a molecule of oxygen containing 3 oxygen atoms. This is not the same as the oxygen we breathe, which has 2 atoms per molecule. Ozone absorbs ultraviolet radiation, which warms the air in the stratosphere. As a practical matter, ozone protects life at Earth's surface from receiving a lethal dose of ultraviolet radiation. Beyond the stratosphere is the mesosphere. Here, temperatures drop to their lowest value in the atmosphere. Only about 0.1% of the atmosphere lies beyond the stratosphere, and the vast majority of that tiny quantity is found in the mesosphere. That means that the air in the thermosphere represents only a minute fraction of our atmosphere's mass. Because the gases in the thermosphere are moving at very high speeds, the air temperature is high. But the gases are so sparse that collectively they possess an insignificant quantity of energy. There is no distinct upper boundary to the thermosphere because the atmosphere gradually merges with the emptiness of outer space. Drag the correct label to the appropriate spot on the graph. When we view the atmosphere from the ground, it seems to be very thick. However, when compared to the thickness of the solid Earth, the atmosphere is a very shallow layer. The lower boundary of the atmosphere is Earth's surface. However, there is no well-defined upper boundary. As we move away from Earth's surface, the atmosphere rapidly thins and gradually merges with the emptiness of space. One way to examine the vertical extent of the atmosphere is to measure changes in air pressure. If we could enclose a 1 square inch column of air that extended from Earth's surface to the top of the atmosphere, it would weigh 14.7 pounds. If this scale were taken to higher and higher altitudes, the weight of the air column would decrease rapidly. As this diagram illustrates, the density of the atmosphere decreases rapidly with an increase in altitude. Modern meteorologists do not express air pressure in pounds per square inch. Rather, they use units known as millibars. The data on this table show the average vertical distribution of air pressure. Plotting information on a graph is a common and helpful way of displaying data. Plot the data for 5, 10, 20, 30, and 40 kilometers on this graph. Drag each point from the table to the correct location on the graph. After all the data are plotted, a smooth line connecting the points is drawn. Use the graph showing air pressure variation with altitude to answer this question. The top of Mount Everest is nearly 9 kilometers above sea level. What is the air pressure at this altitude? If the air pressure at the top of Mount Everest were 300 millibars and sea level pressure were 1,000 millibars, which of the statements is correct? Refer to the graph showing air pressure variation with altitude to answer this question. Which statement is correct? About 90% of the atmosphere is below an altitude of kilometers. In summary, data on vertical pressure changes revealed that the vast bulk of the gases making up the atmosphere are very near Earth's surface, and that the atmosphere gradually merges with the emptiness of space. We know that the atmosphere is an envelope of air that surrounds our planet. But what is air? Sometimes we use the term air as if it were a specific gas, but this is not the case. In a mixture, each component retains its individual physical and chemical properties. If water vapor, dust, and other variable components were removed from the atmosphere, we would find that the composition of air is very stable up to an altitude of about 80 kilometers. Two gases, nitrogen and oxygen, account for about 99% of the volume of clean, dry air. Despite the fact that nitrogen is the most abundant gas in the atmosphere, it is relatively unimportant in terms of most weather and climate processes. Oxygen, the second most abundant gas, is vital to virtually all life on Earth. Most of the remaining 1% of dry air is the inert gas argon. Tiny quantities of other gases are also present. Each of these gases represents just a tiny fraction of 1% of the atmosphere. When tiny amounts are involved, it is common to express concentrations in parts per million rather than as a percent. Carbon dioxide represents only a tiny fraction of the atmosphere, but it is an important component. Carbon dioxide is important because it is an efficient absorber of energy emitted by Earth and thus influences the heating of the atmosphere. In addition to stable components such as nitrogen and oxygen, air includes many gases and particles whose concentrations vary greatly from time to time and place to place. Examples of variable components include water vapor, dust, ozone, and human-generated pollutants. Air pollutants are airborne gases and particles that endanger our health and/or disrupt the functioning of the natural environment. One category of pollutants is primary pollutants. Primary pollutants are emitted directly from identifiable sources and immediately pollute the air. When sources of primary pollutants are examined, the significance of the transportation category is obvious. It accounts for nearly half the air pollution. Another category is secondary pollutants, which form in the atmosphere when reactions take place among primary pollutants. Ozone, the main ingredient in urban smog, is an example of a secondary pollutant. It is produced near Earth's surface when certain primary pollutants react in the presence of strong sunlight. Acid rain is also a phenomenon associated with secondary pollutants. The primary pollutants, sulfur dioxide and nitrogen oxide, react in the atmosphere with water, oxygen, and other chemicals to form mild solutions of sulfuric acid and nitric acid. Acid rain can damage forests and create toxic conditions for fish and other life. Acid rain also accelerates the deterioration of stone and paint and the corrosion of metals. Although air pollution continues to be an important environmental problem, significant improvements in air quality have occurred. Despite substantial progress in reducing emissions, there are still more than 120 million people nationwide who live in counties with monitored air quality levels above the primary national standards. Earth's water is constantly cycled among the atmosphere, hydrosphere, solid earth, and biosphere. Humidity, the amount of water vapor in the atmosphere, is a basic weather element. Water vapor has many important roles in the atmosphere. Tiny solid and liquid particles suspended in the atmosphere are called aerosols. Aerosols originate from many natural and human sources. Volcanic eruptions, soil blown into the air, and pollen lifted by the wind are examples. Smoke and soot from fires and factories are another source of aerosols. Aerosols have important roles in weather and climate processes. These tiny particles act as surfaces on which water vapor condenses to produce clouds and fog. Aerosols can reduce the amount of sunlight reaching Earth's surface by absorbing, reflecting, and scattering incoming solar energy. Another variable component of the atmosphere is a gas called ozone. Most naturally occurring ozone is concentrated between 10 and 50 kilometers above Earth's surface in a region of the atmosphere called the stratosphere. Ozone in the stratosphere absorbs much of the ultraviolet radiation from the sun. Ultraviolet rays are the burning rays of the sun and can be harmful to life. If ozone did not filter a great deal of the sun's ultraviolet radiation, and if these UV rays reached Earth's surface undiminished, our planet would be uninhabitable for most life as we know it. Anything that reduces the amount of ozone in the stratosphere could affect the well-being of life on Earth. The production of chlorine-containing chemicals such as chlorofluorocarbons has led to the loss of ozone in the stratosphere. CFCs gradually drift into the stratosphere, where they are bombarded by the sun's ultraviolet rays. In response, the CFC molecules break up and release chlorine atoms. Free chlorine atoms react with ozone molecules by taking one oxygen atom to form chlorine monoxide and leaving an ordinary oxygen molecule. Then, when a molecule of chlorine monoxide encounters a free atom of oxygen, the oxygen atom breaks up the chlorine monoxide, stealing the oxygen atom and releasing the chlorine atom back to the stratosphere to destroy more ozone. This reaction occurs over and over again, allowing a single chlorine atom to destroy many molecules of ozone. Ozone depletion occurs worldwide but is most pronounced every September and October in the Antarctic region. Here, during spring in the southern hemisphere, an ozone hole develops. A treaty called the Montreal Protocol, concluded under the auspices of the United Nations, calls for a phase-out of CFC use by early in the 21st century. Even though CFCs will no longer be in use, the CFCs that are already in the atmosphere will remain active for many years to come. In summary, air is a complex mixture of many gases and particles. Some components are stable and non-variable, while others vary greatly from place to place and time to time. When describing the atmosphere, we sometimes talk about the weather and at other times refer to the climate. Weather refers to the behavior of the atmosphere at a particular place for a short period of time. For example, this weather map shows that it is currently raining in Florida and northern Indiana, and that the temperature is 76 degrees Fahrenheit in Seattle, Washington, and 96 degrees Fahrenheit in El Paso, Texas. Weather can change rapidly. Sometimes just a few minutes makes a big difference. When we seek to answer questions such as these, we are dealing with the weather. The climate of a place is a generalization of the weather conditions over a long span of time. Although averages are basic statistics in many climate descriptions, variations and extremes are also important. This graph provides useful information about average temperatures in New York City. But knowing the extremes that might occur provides additional useful information. Climate data presented by way of maps, graphs, and tables can provide useful information about a place. About what % of possible sunshine does Amarillo, Texas receive in November? Climate data aids planning and helps us know what to expect when visiting a particular locale. But climate data cannot predict the weather. The nature of both weather and climate is expressed in terms of the same basic elements. The elements are those quantities or properties that are regularly measured and constitute the variables by which weather and climate are expressed.